Episode 72, titled Training Cost versus Inference Cost, Choosing Models for the Real World, the focus is on selecting models that fit compute budgets and latency realities, because the best model on paper can be the worst model in production if it cannot serve predictions within operational constraints. The exam cares because scenario questions often describe real-world limits like response time, budget, or deployment environment, and the correct answer is the model that meets those limits while still improving outcomes. In practice, teams commonly underestimate the total cost of ownership by focusing only on training success and ignoring what it costs to run the model every day. A model is not just a research artifact, it is a service or a batch job that must run reliably, predictably, and safely. When you understand training versus inference cost, you choose models that stakeholders can actually deploy and maintain. That discipline is what turns modeling into an operational capability rather than a one-time experiment. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Training cost is the time and resources required to build the model, including compute cycles, memory, storage, and the engineering effort needed to run training pipelines reliably. Training includes data preparation, feature computation, model fitting, hyperparameter tuning, and validation cycles, all of which can be expensive depending on dataset size and model family. Training cost also includes iteration overhead, because training is rarely done once. It is repeated as you refine features, adjust evaluation, and respond to drift. The exam expects you to recognize that training cost is paid during development and during periodic retraining, and that high training cost can slow iteration and limit how quickly you can adapt to changing conditions. Training cost can be acceptable if training is infrequent and the resulting model is stable, but it can become a bottleneck if retraining must be frequent or if the model requires extensive tuning to stay competitive. When you define training cost clearly, you are setting up the idea that it is a recurring investment, not just a one-time build expense. Inference cost is the time and resources required per prediction, which is the cost that directly determines whether the model can meet latency targets and scale to production volume. Inference includes not only the model computation, but also feature retrieval, pre-processing, and any downstream post-processing needed to produce an actionable output. A model that is cheap to train can still be expensive to serve if it requires heavy feature computation at prediction time, or if it has a large parameter footprint that stresses memory and CPU. Conversely, a model that is expensive to train can be cheap to serve if it compresses well and uses simple features at inference. The exam cares because inference cost is often the limiting factor in real-time systems where milliseconds matter and volume is high. Inference cost also affects reliability because complex serving stacks create more failure points and can degrade user experience. When you understand inference cost, you are evaluating not only whether the model works, but whether it can be delivered on time, every time. Batch inference and real-time inference face different constraints, and the exam expects you to choose models with that difference in mind. Batch inference is typically run on schedules, such as nightly scoring or weekly segmentation, and it can tolerate higher per-prediction cost if the job completes within the batch window and within budget. Real-time inference must respond within strict latency limits, often under unpredictable load, and it must be resilient to spikes and failures, which favors simpler models and simpler feature pipelines. Batch settings also allow you to pre-compute features, cache results, and amortize expensive computations, while real-time settings often require on-demand computation with tight bounds. The exam often signals this through wording like
at point of transaction or during login, which implies real-time constraints, versus daily report or weekly refresh, which implies batch constraints. Choosing incorrectly can lead to a model that is operationally unusable, even if it is accurate. When you narrate this distinction, you demonstrate that deployment context determines what cost profile is acceptable. When latency, explainability, or cost dominates, simpler models are often the right choice because they minimize inference time, reduce infrastructure complexity, and produce outputs that are easier to justify. Simpler does not necessarily mean weak. Well-designed linear models and compact tree models can perform very well when features carry strong signal and relationships are reasonably stable. Simpler models also retrain faster, which supports faster iteration and easier adaptation to drift, and they are often easier to monitor and debug because failure modes are clearer. The exam expects you to prioritize simplicity when constraints are tight, especially in high-stakes environments where transparency and reliability matter as much as small accuracy gains. A simple model can also support clearer governance because explanations are more straightforward and policy integration is easier. When you choose a simpler model under dominating constraints, you are choosing the model that can actually serve the business reliably, rather than the model that only wins in offline benchmarks. Complex models can be justified when gains are large enough to offset added maintenance and risk, because there are settings where improved discrimination yields substantial business value. Complex models can capture nonlinearities, interactions, and subtle patterns that simpler models miss, potentially reducing losses, improving retention, or increasing safety. The cost is that they can require heavier infrastructure, longer training cycles, more careful monitoring, and more specialized expertise to maintain. They also introduce risk in governance and explainability, because stakeholders may not accept decisions from opaque systems without additional validation and controls. The exam expects you to weigh these trade-offs explicitly, recognizing that complexity is an investment that must be repaid through measurable outcome improvement, not through marginal metric gains alone. Complex models also increase the risk of drift sensitivity because highly flexible models can overfit to transient patterns and degrade faster when the environment changes. When you choose complexity, you should do it because the problem demands it and the value justifies it, not because it is technologically appealing.
Hardware and deployment environment limits are practical determinants of cost, and the exam often expects you to reason about CPU, GPU, memory, and where the model will run. If the model must run on commodity CPUs in a constrained service, heavy deep learning inference may be impractical unless optimized and supported by appropriate hardware. If the environment includes GPUs and the scale is high, deep models may be feasible, but you still need to consider memory footprint and latency under load. Memory constraints can matter even more than compute because a large model can thrash caches and slow down serving even if the raw compute is manageable. Deployment environment also includes edge devices, private networks, and regulated environments where hardware upgrades are slow or impossible, making lightweight models more appropriate. The exam will often provide hints like embedded device, high throughput, or limited infrastructure, and the correct response reflects those limits. When you talk about hardware, you show you understand that model choice is also an engineering choice, constrained by real systems.
Comparing tree ensembles versus deep models is a useful practical exercise because these families represent different points on the cost and capability spectrum. Tree ensembles can provide strong performance on structured tabular data, capture nonlinearities and interactions, and often have moderate inference cost that can be acceptable in many batch and some real-time settings. Deep models can excel when you have complex inputs like text, images, or high-dimensional embeddings, and they can learn rich representations, but they often require more training compute and more careful serving optimization. The exam expects you to match the model family to the data modality and the operational context, not to assume one family is universally superior. For many structured business datasets, a well-tuned tree ensemble can deliver most of the achievable value with less infrastructure overhead than a deep model. For multimodal inputs or problems with representation learning needs, deep models can justify their cost, especially when optimized for inference. When you compare these families by operational needs, you demonstrate that you are choosing for real-world performance, not for theoretical appeal. Retraining cadence is a frequently overlooked part of cost because frequent retraining multiplies training cost and can also increase operational complexity. If drift is fast and models must be updated weekly or daily, a high training cost model can become unsustainable, not only in compute but also in validation, deployment, and governance workload. Frequent retraining also increases change risk, because each update can introduce regressions or unexpected behavior, requiring stronger monitoring and rollback capability. The exam often tests this by describing environments with rapid change or adversary adaptation, and the correct reasoning includes considering how often the model must be refreshed to remain valid. A model with slightly lower accuracy but much lower retraining cost may be the better real-world choice if it can be updated quickly and reliably. When you incorporate retraining cadence, you are evaluating total lifecycle cost rather than one-time training expense. The right way to think about value is cost per correct decision, not only accuracy improvements, because operational systems exist to drive decisions with real costs and benefits. A small accuracy gain may be extremely valuable if it reduces fraud loss significantly at scale, while a larger accuracy gain may be irrelevant if it does not change the decision boundary or if it increases false positives that overwhelm operations. Cost per correct decision includes compute cost, labor cost, and the cost of errors, such as customer friction or missed incidents, and it provides a more meaningful comparison across model families. The exam expects you to reason in this way when scenarios include operational capacity, investigation cost, or customer impact, because those are the costs that matter most. This perspective also helps communicate trade-offs to leaders, because leaders care about cost and benefit, not about abstract metrics. When you evaluate cost per correct decision, you are aligning model selection to business outcomes rather than to leaderboard scores. Communication of cost trade-offs should use plain numbers leaders can follow, because cost discussions become persuasive only when they are concrete. Leaders can understand statements like, "This model requires twice the hardware and increases per transaction latency by a measurable amount," or "This approach reduces false positives by a percentage that translates to fewer investigations per day." Even when exact numbers are not available, you can communicate in relative terms tied to constraints such as "fits within our current CPU budget" or "requires GPU serving to meet latency." The exam expects you to communicate trade-offs clearly rather than hiding behind technical jargon, because decision-makers need a narrative that ties model complexity to operational impact. Clear communication also supports governance because it shows you considered risk and maintenance, not just performance. When you communicate cost in plain terms, you increase the chance that the chosen model is supported and sustained. Optimization strategies can make a model feasible when the desired family is close to the constraint boundary, and the exam expects you to know that options exist beyond simply giving up. Catching can reduce repeated computation for common inputs or for entities scored frequently, reducing effective inference cost. Quantization can reduce model size and speed up inference by using lower precision representations where acceptable, trading a small amount of numeric fidelity for large performance gains. Feature reduction can cut inference time by removing expensive-to-compute features or by pre-computing features in batch and serving them quickly at inference. These strategies must be planned with care because they can change calibration and behavior, so they should be validated under the same evaluation design as the baseline model. The exam often frames this as "how do you meet latency?" or "how do you deploy within constraints?" and the correct answer includes both model choice and optimization planning. When you include optimization, you show you think like an engineer responsible for delivery, not only like an analyst.
A helpful anchor memory is training builds, inference serves, both must fit reality. Training is the process of creating the model, and it must fit the organization's ability to retrain as needed. Inference is the process of serving predictions, and it must fit latency, throughput, and reliability requirements. Both must fit reality, because a model that is cheap to train but impossible to serve, or easy to serve but impossible to update, will fail operationally. This anchor helps on the exam because it pushes you to consider both sides of cost, especially when a scenario emphasizes one and distractors ignore the other. It also encourages life cycle thinking. Costs repeat, environments change, and models must be maintainable. When you apply the anchor, you choose models that can live in the system, not just models that can be built once.
To conclude episode 72, choose a model family and justify it by constraints, because that is how exam questions typically test your judgment. Suppose the scenario requires real-time fraud screening at transaction time with tight latency and limited GPU availability, and the organization also requires clear explanations for disputed declines. A tree ensemble, or a regularized linear model, is a defensible choice because it can run efficiently on CPUs, meet low latency requirements, and provide explanations that can be communicated to operations and customer support. You would then focus on feature design that is cheap to compute at inference, and you would evaluate cost per correct decision by quantifying how many false positives are avoided within capacity constraints. If the gains from a deep model are not large enough to justify GPU serving and increased complexity, the simpler family is the real-world winner despite any small offline accuracy gap. This reasoning matches the exam's intent. The best model is the one that improves outcomes while fitting budgets, latency, governance, and maintenance realities. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.